Hello, my name is Paulo Miguel T. Diaz, and this is Complex Mixing Problems for Math 207A. The reason I chose this topic as my presentation is because we did not go over it in class, that first of all. Second, the use of this differential equation is very wide. You can use it in many problems. So, again, complex mixing problems are one of the applications of differential equations used to model a continuous event. Basically, in a complex mixing problem, you have something being poured in, typically a liquid with a solution. Uh, Normally, the math problems would include like salt, and when it is being poured in a tank, it is being mixed, uh, quote unquote, perfectly, and it is also being poured out continuously. Now, as you can see, that's just an analogy. We can basically use this with anything that is being added and taken out. And with that in mind, real world applications, the complex mixing problem differential equation can be used in many real world applications. It has such a wide variety. Um, But for this one, I chose sewage treatment, manufacturing plants, pollutants in a body of water, and drug or liquids like alcohol entering the body. Again, something going in, something going out. That's simple. So now that you have an idea of what it is, something going in and something going out, the model is simply that dq over dt equals q in minus q out, where q dq dt or q prime t is the rate of change, the q in is the rate at which it enters, and q out is the rate at which it exits. For this project though, we will expand the equation and have it be dq of dt equals C1 R1 minus C2 R2, where the C's represent the concentration of the substance and R representing the rate of the substance. And so C1, as you would imagine, would C1R1 would be the concentration and the rate of the substance at which it enters, minus uh, the C2R2, which is the concentration and the rate of the substance at which it exits. Things to consider and assumptions. The rate in, concentration in, and the rate out has to be constant. The reason rate in and rate out has to be constant is much alike. The reason being is because if they are different, if they aren't like a constant number and they're different numbers, the we would have multiple problems. It wouldn't be one single problem; it would be multiple. Concentration has to also be constant because if it changes in the middle, like let's say 60 seconds after, the it would just drastically change the amount of what the solution is and or what's in the container, and it'll just mess up the whole equation as well. The thing that isn't constant though is the concentration out, because that is always changing, because as you can imagine, yes, it is being mixed, but when it's being poured out, we aren't sure if the percentage of the solution and water is the same. So with that in mind, since concentration out is always changing, it has to be something dividing by something. In this case, it would be the amount of solution in the body of water at any time divided by the volume of the water at any time. Q of t over V of t, where Q of t is the amount of solution and V of t is the volume of water. Knowing this, We can replace our concentration 2 out with the equation with that thing. So it'll be dq over dt equals C1R1 minus qt over vt R2. We rearrange this to make it standard form, which is q prime t or dq over dt plus qt over vt R2 equals C1 R1, which is, as we know, a non-homogeneous equation. When we get our values or data, we could use integrating factor or separable equation to get the function and find the solution we're given. So basically, when we're solving for this differential equation, we are finding the function that will tell us the amount of the solution in a certain point of time. That could be 60 seconds, and we will know the amount of solution in that point of time. The example I use is a question which asks, a tank contains 100 gallons of water and 50 ounces of salt. Water containing a salt concentration of 1/4 times 1 plus 1 half sine t ounce per gallon flows into the tank at a rate of 2 gallons per minute, and the mixture in the tank flows out at the same rate. The questions are, find the amount of salt in the tank at any time and plot the solution. So we look at what's given. We have R1, C1, R2, and C2. R1 being the rate, which is 2 gallons per minute, and the rate out is also 2 gallons per minute because it states that they're both, the rate in and rate out is the same. We see that C1, the concentration one, is the concentration of it going in is 1/4, 1 plus 1 half sine t, and the concentration of 2 of going out is qt over 100 ounce per gallon, because we don't know the q of t, but we do know that it contains 100 gallons of water. Plugging in the numbers and simplifying, you get, and moving things around, you get dq over dt plus q over 50, or basically 1 over 50 times q, equals 1 half plus 1/4 sine t. Since it is in standard form, I will use integrating factors mu of t, uh, e to the t over 50, because we know that the p of t is 1 over 50 over, and when you integrate 1 over 50 dt, you get e to the t50 t. I've skipped the work shown here, but basically I use the equation that she gave, which is the 1 over e mu of t plus 1 over the thing plus integral of the 1 half plus 1/4 sine t. And after all the calculation and plugging in what's given, you get q of t equals 25 minus 625 divided by 2501 cosine t plus 225 divided by 5002 sine t plus 63,150 divided by 2,501 e to the negative t50. That is the, as you can see, that's the 1 over, but it's, again, simplified it to look like that. When graphing this function, you can see that the solution is slowly decreasing as you go with the time. And yeah, that's basically what we have. It is slowly decreasing. So the conclusion and importance, as you can see with the complex mixing problems, we can calculate a solution of something and calculate the concentration of that, or like the amount of the solution in a certain point of time. And with that, with knowing that, we can use that to observe many things in real life. Again, it is a good way to calculate the concentration of the solution in a liquid that is continuously moving. And such as we can use this in many real world applications, such as again drug entering the body or pollutants in a body of water. As for the future of this, um, I could only see it being used the same. There's really not much improvement that it needs, because we're already using it in our everyday lives. This is my reference page. Thank you for watching. I hope I will do well.